All right. Today's lecture is going to be about another statistical test that is called analysis of variance, and it has an abbreviation ANOVA, A-N-O-V-A. It is a test in which we are comparing the means of multiple populations, not just two, but possibly 3, 4, 5, and more. As a matter of fact, of course, you would not use this test for the comparing a mean of two populations because you already have another test for that, a Z or T test that we did in the past. So you would use this test when you have more than two populations in general. And I have one example with 3 populations here, but you could also have many more than that. This test is mostly an indicator test, meaning that once the test is confirming rejection of a null hypothesis, you probably want to do some more testing in regard to what the test is telling you. So it would usually not be the end of the story. So the assumption that we make to use the ANOVA test are that all of the populations are distributed normally, which is usually not too hard to get. Then the samples are also drawn random samples and they're independent. That's another thing that we have met in the past, so that's not too hard to do either. And the third thing, it would be to assume that population have about the same variation. Now that's a little bit harder to get. It might not be true, but we are routinely going to assume that, and then again, when the test is concluded and we had the rejection of a null hypothesis, then we would probably going to do another test just to make sure that we didn't get something wrong. Okay, so the setup of the test is very simple. So here I have the 3 sets of blueberries, like a 3 group of plants, and then I was getting the yield from each of those, and I was calculating how much I'm getting. Now why would I have 3 sets of blueberries? Well, it could be different reasons, but I want to compare here fertilizers. So I was using the same species, the same cultivar, and I was getting the fertilizer type 1, the fertilizer type 2, the fertilizer type 3. So I have a blueberries in this first group. The first blueberry gave me 16 pounds of blueberries. The second one 14, and then I had 13 pounds, 15 pounds, 11 pounds, and 15 pounds. On average in this group, I got a 14 pounds per plant. Right? When I was using the fertilizer number 2, I got the first blueberry 18, then 15, 15, 14, 12, the last blueberry 16 pounds, on average 15 pounds. And in the third group, I use the fertilizer of another type, and I got 21 pounds, 15 pounds, 12, 18, 17, 17 pounds. On average 16.6 with a bar, so that's 16 and 2/3 pounds. So you can see that I have the difference here, and looks like the fertilizer 3, the third type of fertilizer, gave me the best yield. I had the best crop. So the question is this significant, right? Is there a significant difference that I have here between any two? That's the story. So I'm comparing 3 types of not really types of a blueberry, but I'm comparing the usage of 3 types of a fertilizer with the same blueberry. And I am trying to figure out whether I have any difference in using this fertilizer. So we also call this fertilizer factor. So I have a factor, fertilizer number 1, fertilizer number 2, fertilizer number 3. That's a factor group. 3 different fertilizers. And then of course I have these blueberries themselves. I have 6, 6, and 6. You don't have to have 6, 6, and 6. It would be depending on what you have. Might be different number in different groups. but I do have, in this particular case, 6 in each group. All right. So the setup of the test would be, the null hypothesis is to assume that each mean is the same. In other words, there are no difference in the mean yield regardless of what fertilizer you use. The alternative hypothesis would be a negation of that. At least 2 are different. Now, okay, so now I have one warning here, because people tend to write stuff like this. Me1 is not equal to me2 is not equal to me3. This is nonsense. In other words, you're claiming here that the first one is different than the second one, and the second one is different than the third one. But you have no idea what happens between the first one and the third one. This is not alternative claim. Okay, this is just one particular thing. I could also say the first one is different than the third one, and the second one is the same as the first one. That would also be different from this. But it's not written here. First one is different than the second one, right? That's what is written. So if I say the first one is different than the third one, but the first one and the second one are the same, that is also negation of this, because this one says the all 3 are the same. So this is something very specific. What you're claiming here is the first one is different than the second one, and the second one is different than the third one. We don't know anything about how related the first one and the third one are. They might be the same, or maybe not. So again, don't write stuff like that, because this is not really alternative to this. This one says all 3 are the same. The only alternative we can write here is that there is difference between 2. So you can write it verbally. There is difference between 2 groups, 2 means. Which, I don't know. Maybe the first and the second, maybe the second and the third, maybe the first and the third. That's a proper statement. Right? If this is not true, then they're all 3 equal. So this is actually a proper negation of this. Now you might want to write it down. Either this one is different than this one, or this one is different than this one, or this one is different than this one, or they're all 3 different. You see there are 4 different things you could have here. The first 2 are different, the last 2 are different, the first and the third one are different, or all 3 are different. Which, of course, is a part of the first, second, and third alternative. But that's kind of a lengthy thing to write. So you can just simply write verbally. There is difference between 2 means. Which 2? We don't know. And ANOVA will not tell you which 2. Okay? Even if you succeed to reject the null hypothesis, you will not have a conclusion which 2. You will only know that there is a difference somewhere. Now which 2 are different? We don't know. But then you take a look here. We will also have something out of that calculation, but you can take a look at it here. Where do you see the biggest differences? You can see number 1, number 3, 14, 16.6. So your next step is going to be, well, let's do the test between this one and this one. That's the test we learned on the last lecture. So you would continue, and now you would do another test. You can say, what's the advantage here? Well, you spare yourself from one test. Because if you test everything here, you're going to have 3 tests. This compared to this compared to this, and this compared to this. That's a 3 tests. Now if you have 4 groups, you have 10 tests. Six tests. You compare the first, second, first, third, first, fourth. Then second, third, second, fourth, then third, fourth. That's 6 tests. If you have 5 groups, it will be 10 tests. And on you go. So, instead of having that many tests, you just do the ANOVA. And once the ANOVA tells you there is a difference somewhere, now you have to find out where. And that would be another test. You can do that straightforward If you find there's a difference here, you compare the first one and the third one, because that's what the difference probably is. Or there is another test called Sheffy test. We're going to talk about it the next time. So this is only the part number 1 of the ANOVA lecture. We have one more lecture to go. But this is the setup. The null hypothesis, we are assuming that the yield, whether you use the fertilizer 1, fertilizer 2, or fertilizer 3, makes no difference, it's the same. Alternative, there is difference. Now, what's the test statistics, or the test value that we often use? Okay, I'm gonna write that one down for you, because it's really a nasty one, nasty calculation. It's this one. Double fraction is a numerator which is a fraction and denominator which is a fraction. Okay, so and there is a meaning to that. Okay, so it has a numerator and it has a denominator. By the way, this lecture of course is on the blackboard, so you want to check it out. I wrote it and I call that particular formula 1.1. Okay, the numerator we call mean square between the groups. Denominator we call mean square within the groups. We also sometimes call that variability between the groups. Variability within the groups. Right? Let me explain that what that means. Here the I represent 1, 2, or 3. 1, 2, 3. So you calculate for 1, you calculate for 2, you calculate for 3, and this is a sum you add. Okay? So xi is x1 or x2 or x3, a mean of a group. X bar is an overall mean. So you have 18 blueberries, the overall mean is 15.222, that's approximation. Okay? Now the difference between the mean in the first group and overall mean, that will be there if there is some difference between the groups, right? Because then one group is going to go a bigger yield, another group is going to give you lower yield. So there'll be some difference here if there is a difference between the groups. So this number, oh, I forgot to put a square here, sorry. This number plays a role. If there is a difference, you will get that number bigger. Then of course this ought to play a role because it's how many things you have in the group. Because if the group is bigger, it's more important than the group that is smaller. And the k is the number of groups. So in this particular case, k is equal 3. You have 3 groups. So basically we are finding the sum of squares between the group, like you're calculating the standard deviation, that's what we do there. And then we average that, how many groups we have. You have 3 groups, but we average by the degrees of freedom. Degrees of freedom between the groups is 2. There are 3 groups. Okay? What we have downstairs is just the straight old variability. You have the standard deviation. Standard deviation squared is the variance. So this is variation in the first group, second group, and third group. And again, depends how many things you have in the group. You have more things in the group. The variation in that group has to play a bigger role in your overall calculation. So that's what we're doing here. And then you're dividing with the overall degrees of freedom. So we are pulling them. You have 5 degrees of freedom, 5 degrees of freedom, 5 degrees of freedom, that's 15. Or you can just simply say n, which is 18, overall number, minus 3, which is 15. So you're subtracting 1 degree of freedom for every group. So that's what we are averaging at the bottom. So what you have on the top is the variability that is from group to the overall mean. So whether one groups go further from the overall mean or no, that's going to play a role here in this number. The more groups deviate from overall mean, the bigger this number is going to be. And again, this is called mean square between the groups. Alright, so I'm going to write piece by piece. So the numerator of the numerator is called the numerator is called sum of squares between the groups. So it's usually written sum of squares between the groups, like that. Okay? Now do you calculate that? It's not too hard. I mean, you have to do the summation for every piece here. So you have to do the n1. n1 is 1, 2, 3, 4, 5, 6. The I forgot the bar. The mean in the first group, 14, minus the overall mean, 15.222 squared. Second group, 6. There's 6 things in the second group as well. Mean in the second group, 15, minus the overall mean, okay, and the third group, 6. The mean in the third group, 16.6, bar, minus the overall mean, 15.222 squared. So this is the numerator of the numerator. The numerator itself is a fraction, so you have a numerator here. So this is going to be, you can use a calculator, it's not that difficult to calculate. I got 21.78 something. 21.78. There's a more decimals, you can check it out in my lecture. It's written down, you can find it out there. Okay, now k minus 1 of course is 2. The k is the number of groups. K, 1, 2, 3. So you got k minus 1, which is 2. So now you have mean square. You're averaging now. Mean square between the groups. That number over there, sum of squares between the groups divided with k minus 1. This is the mean square between the groups. We also call that very often variability between the groups. So again, this is the variability from group to group. Okay, if you divide this guy with 2, you get the 10.89. Okay, and this is your numerator here. Now you have the same story, or the same, not the same, but similar story for calculation on the denominator, which is a fraction. So you also have here some kind of sum of squares here, and then you get the average. So we call this sum of squares within the groups. So that's the numerator of denominator. Okay, that we're going to write piece by piece. So I have the number of things in the first group minus 1, that's degrees of freedom, so we have 5, and then we have to multiply that with the variance 1.789 in the first group, and then the same thing in the second group, 5 degrees of freedom there, variance is 4, 2 with the power of 2, and the third group, degrees of freedom 5, the variance in the third group is 3.011 square. And again, you have to use a calculator, and I got 81.33 here, approximately. That's just the numerator of the denominator, this piece here. So again, every group, number of degrees of freedom times the variance. First group, second group, third group, and then you do the sum. That's the formula it's telling you to do that. Now I have to average it, so I'm going to divide that with 15. This is 18, the total number, and minus the k, the number of groups, which is 3. So I have to calculate now mean square within the group. So this is the mean square within the group. This is the mean square between the groups. This number here, sum of squares within the group divided with n minus k. And that would be 81.33 divided by 15. I got something like 5.42. Okay? That looks like a very unpleasant calculation. And it is a pleasant calculation. But you have to do it. So, because of that, we want to actually have this summarized. And we make the summary here, so in a table, a typical summary we do. So I'm going to erase them. I'm going to write it again in a table without now this extra calculation. Since we've done the calculation, so you can have it on a scrap paper, right? Before you make a summary table. So summary table looks like this. We have the bunch of things that we're going to summarize. Okay? We're going to have the degrees of freedom. Okay? And we are going to have the two things between the groups and within the groups. So we have we call that factor, or sometimes treatment. You have, you're treating three groups of blueberries with different fertilizers. That's a treatment. Or you can say the fertilizer is factors. So factor 1 group, factor 2 group, factor 3 group. So that makes perfect sense. So associate this with between the groups. Okay? So factor, how many degrees of freedom you have? You have 2 degrees of freedom because you have 3 groups. Then you have the general variability within the groups, which we will call a noise or an error. So we usually write an error. So this is your variability, your overall variability within the groups. There is some natural variability from blueberry to blueberry, right? So you can call it a noise, an error, because not every blueberry is going to give you the same. So that's natural variability. We call it error. It's not an error, it's just a natural thing. Natural variability. So we have 15 degrees of freedom. Again, we are pulling 5 degrees of freedom, 5 degrees of freedom, 5 degrees of freedom, total 15 degrees of freedom. Sometimes we write the total. Okay, this is not relevant, but you could do that. 17. Then you write a summary for the sum of squares. Sum of squares. Now you notice I already calculated that. Sum of squares between the groups, and I said it's going to be 21.78, so this is approximation, of course. And sum of squares within the groups, and I call that 81.33. So this is something I calculated. Sum of squares between the groups, sum of squares within the group. Okay, factor between the groups, error within the groups, total stuff. Okay, now the next thing is the mean square. Mean square, you divide this guy with this guy. That's this divided with this, so it's a mean square between the groups, factor between the groups, and I got 10.89. And mean square within the groups, and here I got 5.42. Right, all of that calculation has been done already. You could add all of those numbers, it's irrelevant. So you can go without this third row completely, you don't really need it. But we usually add sum of squares, so I got 103 here, and I don't know, like 103. Sorry, point, I think it's like 11, something like that. I'm not gonna add mean square, it's fine. I don't really need it at all. Okay, finally, you need to calculate the test value, which is mean square between the groups divided with mean square within the groups. Mean square between the groups divided with mean square within the groups. So this is your, what we call a test value. Now you could call it test value or test statistics, but it's more often called F value. I'll tell you in a moment why. Okay? 2, approximately. When you divide this with this, actually it's a little more than 2, so I don't know, maybe like 2.1 or something like that. I got 2.08. I wasn't very precise in calculating this stuff here. This was, I was having here, excuse me, 4.2. I made a mistake. 5.42, not 2.2. You have to be a little careful with that calculation. It just plays a big role if you make a mistake in a decimal, and then you keep on dragging that mistake further on in all other calculations. So that's how it looks like. Okay, this test value or the test statistics we call F value. It's not the Z value, it's not the T value, it's not the chi-square value, we call F value. The kick is, what you're comparing here is the variability from group to group versus the overall variability. So now, if there is a variability from group to group that plays a role versus the, I mean, you have some kind of fertilizer that plays a role and makes a difference, then this number is going to be important. It's going to get bigger compared to the, you know, just simply regular variability, and then this thing is going to become bigger. Which means that you will be able to say, hey, I have something going on here. It looks like, you know, from fertilizer to fertilizer, I have something important going on, something that, you know, introduced me to a bigger variability versus the typical variability I would just have from blueberry to blueberry. Apparently I have variability that is between the groups. From one group to another, there is some difference. Okay, so that guy Fisher, we have one lecture about him, was investigating what kind of distribution could be associated with this thing here. So he come up with a Fisher ratio distribution. That's another distribution. It's not a t distribution, not a z distribution, not a chi-square distribution. It's just another distribution. And we have tables for that. And it's a sort of complicated distribution because it depends on 2 degrees of freedom. On degrees of freedom between the groups and degrees of freedom within the groups. So the tables are quite big. You will find that in the handout. I have a handout there for the end of the, well, actually at the bottom on Blackboard in that menu you will find the handouts and you will find the Fisher ratio table. The Fisher ratio table will give you 4 different tables for different level of significance. 1 table and 2 pages is for the 10% significance, or then another 2 pages for 5% significance, then another 2 pages for 2.5% significance. We didn't have that in the past, but we'll have it here. And another 2 pages of tables for 1% significance. So you could have more, but we're not going to have anything more than that. Okay? Now, just like some other tests that we had in the past, this test is only a right tail test. Why? Because we are only interested when this is really getting bigger relative to this. Because then we have a difference here. Now, if this is not getting bigger relative to this, that means that variability between the groups plays really not much of a role. Then we could just say, oh, how perfect this is. It doesn't matter what fertilizer it is, it's just about the same. Now, we're not interested in that. We are never going to work to affirm this. So we are not interested in affirming this. We are only interested in rejecting this. Or we're going to say we don't have enough evidence. So to reject this, you need to have this number much bigger than this number. So the whole value becomes bigger. Now if you have that, then you're going to be rejecting the null hypothesis. So we're only interested in getting the right tail, getting this thing bigger than this one here. So the test is only a right tail test. Again, the left tail test would only mean that, oh, how perfect this non-importance of the fertilizer would be. And we are not really interested in that. So we're not testing whether the fertilizer is not important. We are testing whether the fertilizer is important. Okay? So remember that. So that's the right tail test. Okay. Now, so Fisher did this investigation, so he concluded that this thing here, based on those assumptions I made in the beginning, independent samples, the same variability so that we can pull, and every one of the yield distributed normally. That's happening here because when you take the blueberries, you will see that distribution from blueberry to blueberry will be normally distributed. So equal variability, that's a little bit different problem. It might not be there, but we are assuming that. In either case, if you have those assumptions satisfied, then Fisher said this is going to look like very similar to the chi-square distribution, but not quite. All right? So this one in particular will have this kind of look. So obviously this number is always going to be positive, right? Square, everything is positive, square, everything is positive here, so you're going to get a positive number. So it starts with 0, and it could have a hump and go further, or it could just start from the beginning like that and then go down there like this, something like that. But it has a 2 degrees of freedom between the groups and within the groups. So it has, this one is 15 degrees of freedom. And if you have something else, then changes. Shape would be a little bit different. All right? So it has a 2 degrees of freedom. So this is called Fisher ratio curve. Fisher ratio curve. Or a Fisher ratio distribution. It looks like sort of like a chi-square, but it's not really chi-square. All right? So now, what's your rejection criterion? Just like every time we had in the past, we are looking for thing to be in the tail. This value. I just calculate that, so this is all calculation give me that I got this approximately 2. Let's just say 2. Okay? So now the question is, so my picture goes over there because I didn't want to crowd it here. So the tail. What tail we're gonna use? We're gonna use our standard story about the level of significance. When we don't have anything better, we use 5%, right? Okay. So now you're gonna have to find this table. So I already said you have 8 pages of the table: 2 pages for 10%, 2 pages for 5%, 2 pages for 2.5%, and 2 pages for 1%. We are going to use 5% level of significance. So I'm looking for this value here. Where is the start of the tail? And that tail is supposed to be 5% here. And again, the curve is supposed to be 215 degrees of freedom Fisher ratio curve distribution. There's a 2 degrees of freedom and 15 degrees of freedom. There's 2 types of degrees of freedom. So when you find this table, and you're going to open the blackboard where that table is, and you will find the first degrees of freedom will be on the very top. There's going to be like a table like that, and you're going to have to find that's 5 degrees of 5 level of significance, 5% level of significance, and you're going to have degrees of freedom number 1, and then it's going to be 1, 2, 3, 4, da da da. You're going to be looking for 2, and then on the side you're going to have, well, excuse me, yeah, it starts with 1. Yeah, you might wonder, why would you want to do the test with 2 population when you can have that old T or Z test with 2 population? Yeah, that's usually not done. But if you want to do ANOVA with 2 populations, you can still do it. Okay, it's kind of interesting to compare what you get with that old test that we have between 2 population means, and now with this new ANOVA test with 2 population means. Again, we will usually not use that, but the tables do have that degrees of freedom starting with 1 and degrees of freedom number 1, and then starts with 1, 2, 3, and on you go in the tables. And then you also have degrees of freedom number 2, and that starts with the also 1, and then you have a 2, and on you go. And what we need to find out is 15. So somewhere down there is 15, and so you're going to find degrees of freedom between the groups 2, degrees of freedom within the groups 15. In the tables for 5% level of significance, and I'll tell you what that is. I have that number to be 3.7389. I found it in the table, so it's going to be here. 3.7389. Alright? I made my table really small so you can hardly find it. You can hardly see what I wrote, but it's 3.7389. Alright? That is where 5% in this distribution starts. Now take a look. What's your test value? Your test value is here. It's not in the tail. The tail starts at 3.7, and your test value is a little more than 2, so it's not in the tail. In other words, you cannot reject this. There is no rejection here. No rejection. No rejection of H0, which is actually properly stated. We do not have enough statistical evidence to claim that fertilizer play a role in the yield of blueberry. And you say, how is that so? I can see clearly here 14 and 16.6. Well, remember what the story is about. The story is about statistical evidence. You have a 6 blueberry and 6 blueberry here. that might not be enough to claim statistical evidence. So if you really do believe that fertilizer number 3 is a better fertilizer and it will give you a bigger yield, then prove that by getting more blueberries in your sample. In which case, you might have the same situation, but the test will have enough statistical evidence to prove the difference. So, in this story here, the difference that we are getting here, based on how small our samples are, is not enough difference to claim statistical evidence of difference. In other words, we do not have enough statistical evidence to claim that the means of blueberries versus the different fertilizer would be different. Okay? Again, if you really do believe there is difference in terms of a treatment here, that's why we call it factor or a treatment, the factor plays a role, then get bigger samples and prove that with bigger samples. Maybe you will be able to, but at this point you don't have enough evidence. So again, like in many of our tests in the past, the size of the things in the sample plays a role. So I mean the size of the groups. If you don't have enough blueberry plants here, the difference just could be random, right? 6 versus 6, I don't know. Maybe you have one blueberry that is really much better than the rest, and then that blueberry actually makes the whole of a difference there is. And that would not make any difference what the fertilizer is. So you could have this situation easily. So basically you don't have enough evidence to claim the difference. Okay? Let me go another example. I have students sitting usually in a different rows, right? So we have in the class, when you get in the class, too bad I don't have a class, I just have this online situation here. But when you have a class, you have the 5 rows of seats. So I ask myself sometimes whether the seating makes a difference in terms of our success of students. I'm saying, do better students sit in front or behind or in the middle? Could I recognize the good students already where they sit? Right? I don't know, probably not. But I don't know. That's a good investigation. So here is a little preliminary situation in the beginning. So I have a bunch of people in the class, and I have the row number 1, row number 2, row number 3, row number 4, and row number 5. Okay? So I have students here in those different rows. In the row number 1, I have 3 of them. And now we are taking the preliminary algebra quiz, like a 10-question quiz. I give them 10 questions to see what do they know before they come to algebra class. And the first students have, in row number 1, all 10 answered correctly. The second one got 8 right, and the third one has only 3 right. Okay, that's row number 1. Row number 2, I have the first student 8 right, the second student 5, then another one 4, and I have 2 more students in this row. One guy got 10 right, everything right, and the another person has 5 right. Okay, so this is what kind of table I have. In the third row, I have 5 people too. 2, 5, 8, 1, 3. So this student number 5 in the third row, he's got only 3 correct answers on the quiz. In the fourth row, I have 4 students. And the first student got 8 correct answers, the second student 6, the third student 8, and the fourth student 3 correct answers. And in the last row, row number 5, I had one guy who has no clue about anything we are doing, and somebody who got 2 correct answers, somebody who got 5 correct answers, somebody who got 3 correct answers. Hey, I can see that in the last row I have people that don't know much, right? So maybe I can already make that conclusion. But we're gonna do the ANOVA test here. ANOVA test. So first of all, I need to get the averages. Average in the first row is 7. The first row, the students have an average of 7 correct answers. In the second row, the students have an average of 6.4. In the third row, the average is 3.8. See, I'm not calling that X, Y, and whatnot. I'm having a bunch of them, so I'm going to call X1, X2, X3, and so on. And the fourth row is 6.25. And the last row, really bad, that's 2.5 average. So you could do the scientific conclusion here. Yeah, of course, the people in the first row are much better students than the people in the last row. But this is so, because I really have just 3 students here, and this guy would make all the difference, and maybe this guy too, I don't know. And the last row, I have this guy who is just basically not making the grade, right? I don't know, maybe there is the second guy too, I don't know. But is that enough? 3 versus 4 students, I don't know, right? And now we have variabilities. We have the variance in the first group. I got that 3.606. I have to square that, that's just a standard deviation. Then I have a standard deviation in the second one, 2.51. And then I have a standard deviation in the third one, 2.775. This is approximation, of course, so I have to be a little more careful. The fourth row, 2.363. And the last row, I have the variance, the standard deviation 2.082. Okay, you have to calculate all of that. Okay, I'll tell you later. We're gonna have one Zoom meeting which I'll show you how to do that by using the calculator. But of course, standard deviation you can calculate, and you should be able to calculate, right? That's what you learn in statistics 103, that's statistics 1, so it shouldn't be a problem for you. But you have to calculate. And you have an overall mean as well. So the mean on the quiz, all of the students. So I have 3 plus 5 plus 5 plus 4 plus 4, that's 21 students. So out of 21 students, I have the overall 5.095, the overall mean. Not a great mean, they get about 5 correct questions out of 10, on average, all of them. Okay, so now we're gonna do the calculation here. And we're gonna do the summary table here. So calculation over test value is by you make a summary table here. Yeah, I'm gonna do that piece by piece, but you need to make a summary table. Okay, so I have, again, I am going to have degrees of freedom. I'm gonna have the sum of squares, and I'm gonna have the mean square, and I'm gonna have the F value, the test value at the end. Okay, and I'm gonna have that for a factor. What's a factor here? Well, the seating, which row you're in. Row 1, row 2, row 3, row 4, row 5. That's a factor. It's also called treatment, like treating students with seating, right? And then you have the what we call a noise over an error. Any class of students you have, there will be variability from students to students. So that's a typical variability. So now the question is this seating factor introduces an extra variability than the regular one, right? So which means that where the people sit will have an impact on their knowledge. Or it's related to their knowledge, right? But in either case, would that be a difference in seating? So now the setup of my test would be that all 5 rows have the same mean. Null hypothesis. The alternative hypothesis, there is difference between 2 means. There is the difference between seating in 2 rows. Don't know which one, which 2, but there will be a difference between 2 rows. And again, don't write this with all of the not equal, not equal, not equal, because that would mean that you want to say, oh, first is different than second, second is different than third, third is different than fourth, and fourth is different than fifth. But how different is second and fourth? I don't know. So don't write that. So just write, there is a difference between 2 means. Which 2? We don't know. Okay? Is that seating going to be different knowledge associated with seating? Okay, degrees of freedom. Well, for 5 groups, degrees of freedom in between the groups, or we call it degrees of freedom for factor, is 4. Degrees of freedom for error is 17. That's n minus k. The total number I have 21 students, 3 plus 5 plus 5 plus 4 plus 4, 21. And the 5 groups, I don't know how to subtract, would be 21 minus 5. So we have 16. I'm pulling degrees of freedom, so you can do it this way. 2 plus 4, 6, plus 4, 10, plus 3, 13, plus 3, 16. That many degrees of freedom. Now sum of squares. Oh, that is not a tricky calculation at all. But, so I'm not going to do it all. You can find it in a lecture. So how that starts? First, sum of squares here. Sum of squares between the groups. You're calculating this guy, the numerator of the numerator. So you will start n1, n2, n3, n4, n5. n1 is 3. Mean in the first group 7. Minus overall mean 5.095. Square it. Plus. Repeat this for the second group. 5. That's n in the second group. And 2. And then the mean in the second group by the overall mean squared. So I got 6.4 minus 5.095 squared. Plus. You have 3 more groups to do. I'm not going there. But once you finish that and you add all of that, you'll end up with, let me check this out, 60.06. That number is going to go here. Sum of squares between the groups. 60.06. Alright? You can immediately finish this story for the mean square. 60.06 divided by 4 is 15 point. So now you get the whole numerator, right? You divide this, what you just calculated as 60.06 with the 4. Okay, 5 groups minus 1, 4, right? And you divide that, you got 15.01. Approximately. You can say actually 15.02. Let's pretend like we are approximating with 2 decimals here. That's what I got. As a matter of fact, in my calculation I got this a little more precise, so it was actually like 1.5. You know, when you have this 5, it's really hard to, you know, I know it's rounding up, but it's really hard to do it. It's best to leave the 5 rather than rounding. So I have 3 decimals here. Okay, now I have to do the sum of squares within the group. So which means this guy, numerator here of denominator. How that goes? Sum of squares within the groups is degrees of freedom, first group, 2. Variance of the first group, 3.606 square. Second group. So I'm only calculate this piece, right? Second group. Degrees of freedom, second group, 4. Time variance in the second group. You have it here. 2.51 square. And now you keep on repeating that. Group 3, group 4, group 5, da da da. You're going to finish this calculation. And if everything is done correctly, you should end up, I got 111.76. So that is a significant number here. It's a big number here. So it goes here. So 111.76. All right. So you write that here. This is your sum of squares for the error, or within the groups. Now you divide this guy with this guy, because you want to get sum of squares within the groups divided with pooled number of degrees of freedom, which is 16. So I could have written here the total, excuse me, 20, right? I don't really need that. So this divided with this, I'm plugging in here, and that's my mean square within the groups, or sometimes called, you gotta remember that because you might have that in homework, variability within the groups. But our proper name is mean square within the groups. And I got 6.99 approximately. And finally you have the whole thing. This is the numerator right here, 15 something. Denominator right here, 6.9, or I could just write 7, right? Now divide this one with this one, and you have your test statistics, Fisher ratio test statistics, test value, test statistics, Fisher ratio value you come up with. Something like 2.15. Okay, that's it. Your summary table. Now this is the thing that you are interested in. That's the test value, right? So you calculate degrees of freedom. It's the calculating degrees of freedom is really peanuts. But then you have to do the sum of squares for both between the groups and within the groups, and then you go to mean square, and now what we are looking for? We are looking for how big is this versus this. Whether this between the groups introduces more variability than you would expect just within the groups. Just normal variability from student to student. Okay? Now if that is so, then you have reason to claim, hey, there's a difference in seating in a row, not just from student to student. And that difference in seating means the students that are sitting in 2 different rows are having 2 different types of scores. I'm not talking about the sample of 21, of course it is. I'm talking about in general, because you want to apply this sample on general situation, that students that are sitting in the first row are better students everywhere than the ones that are sitting in, let's say, I don't know, 5th row. I'd like to say this and this is different, because if there is a difference somewhere, it's going to be between this and this, because that's the biggest difference here in the sample, right? So, rejection criterion. Rejection criteria is based on what? So I'm going to erase this because it's going to impede my picture. So rejection criterion, right tail test, always. F test, or I shouldn't say F test, should. ANOVA test is always right tail test. So you're going to do the picture of Fisher ratio distribution. So I should write it here, but I'm going to do it here because I don't have enough space. It always starts with 0. And this one in particular looks very nice. It's actually very similar to the chi-square curve, but it has 416 degrees of freedom. These degrees of freedom is 416. Has 2 degrees of freedom. 4 for a factor degrees of freedom and 16 for error degrees of freedom. Or should we say between the groups and within the groups? Okay? Between the groups, or factor, or treatment, within the groups, or error. That's a synonymous. So you can say sum of squares for factor, or you can say sum of squares between the groups. You can say degrees of freedom for error, or degrees of freedom within the groups. So get used to that. Between the groups, synonymous with factor or a treatment. Within the groups, synonymous with error. Right? This guy is really fair. I'm sorry, but that's the statistic jargon. And when the statistician uses the jargon and you're doing statistical work, you have to get used to the jargon. All right. So what am I having here? What am I going to use as level of significance? You know what? Let's change a little bit the story because we're using 5% all the time. Let's use 10%. So I'm going to use a 10% level of significance, which means I'm looking for a right tail that will have 10% here. 0.1. Okay? I need a critical value here. I need this value here. So now again, you're going to be looking at the Fisher ratio tables. And you're going to look for first two pages, because first 2 pages are for the 10% level of significance. All right. So again, you're going to look at the top row is going to be degrees of freedom for between the groups. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. What are you looking for? You're looking for 4. And then on the side, you're going to be looking for degrees of freedom within the groups. 1, 2, 3, da 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 da. The one you're looking for is 16. So in the crosshair of these 4 and 16, you'll find a number that I found, 2.33274. It's that precise. They have 5 decimals there after the floating point. And what do we have? The test value. Almost there, not quite. Almost to the tail, but not yet there. I guess I just need a couple more students here. So again, I have the same conclusion as before. I cannot reject this. I don't have a statistical evidence to claim the students in the different rows would be different algebra students in terms of a success. I don't know. I don't have enough evidence to do that, even with the 10% significance. So I'm really relaxing this. So I'm allowing myself to make a bigger error here, 10% significance, but I'm still not able to claim that there is a difference from row to row. Yes, in my sample it is, but again, we're not really testing what is in the sample. We're using a sample as an evidence for general population. We are testing a population means, not a sample means. Sample means, of course, are different. They're all different, right? So the test is about a population means. You're not testing whether there is a difference in sample. I mean, you're blind to see there is a difference. But I don't have enough evidence. I don't have enough students, most likely. Or maybe there is no difference, really. Maybe if I have 300 students, I might not be able to find any difference. I might not have enough statistical evidence for difference anyway. But I definitely don't have it here, okay? So you have 2 tests, 2 ANOVA tests that we did, and both of them were inconclusive. At the end, I didn't find rejection of a null hypothesis. Inconclusive means I didn't reach any decision. I just said I don't have enough evidence to reach any decision, basically. Okay? So the question is, all right, so what was this about? Okay, the next time we meet, in part 2, I'll show you another example when there will be evidence of difference. And in that case, I'll also show you 2 other things. I will show you how to find where the difference is. So when you have the difference, you could go, blind, and you could say, oh, okay, it must be between this one and this one, and first and the 5th group. And now I'm gonna do the t-test. You have normal population, unknown population standard deviation, so you're gonna do the t-test for 2 population. And if that one says, yes, there is a difference, then you have it. ANOVA tells you that is where it is, likely, and it doesn't tell you where it is. It tells you you have difference somewhere, and you're thinking about it, oh, difference between this and this probably, and then t-test says, yes, there you have it. Okay, so we're gonna do that next time. Not in this test. This test doesn't have evidence of difference. But the next time I'm gonna have an example which will have that. And I'm also going to show you another thing. I'm gonna show you how to use your calculator to get the ANOVA test, which will spare you from this nasty calculation, because you have to do the calculation of this guy, then you divide that, put in the table, calculation of this guy, divide with this, put it in a table, and then you divide numerator and denominator to get a final value. And yeah, of course, when you have lots of stuff, and plus of course you have to calculate this, you have to calculate standard deviations and variances. All of that is a very good chance to make a mistake somewhere. So it's a really nice thing to have a calculator to be able to do all of that like that. And of course, calculator is capable of doing that. So I'm going to show you that next time as well. Right? So I'm done with this lecture, but we are not done with ANOVA yet. This is just introduction. We have 2 examples, and we have the setup of the test. But the next time I'm going to show you how that test works if you do have a rejection, and what do you do when you do have rejection, because ANOVA does not tell you ever where the difference is. It will just tell you there is a difference between the 2. If you reject a null hypothesis, the alternative hypothesis, there is a difference between 2. Now which 2? That ANOVA will not answer. You will have to do another test for that. So we're going to do that next time around. Okay? I'm going to end the stream. I hope you're going to watch this, and more importantly, you're going to read and do ANOVA tests in your homeworks, which is the last homework you're going to have.